All right, we're back with part 3 of our DSP discussion. So this is the pop quiz on sampling. We talked about how I'm looking at 501 samples of the sound file, and it's been sampled at a rate of 44,100 hertz. So how long will those samples last? Don't know if you've figured this out or not, but the logic is that basically a second is going to last for 44,100 samples. And we have 501 of those samples, so you divide 501 by 44,100, you wind up getting about 0.01136 seconds or 11.36 milliseconds. You kind of already knew the answer to that, though, because I was plotting time on these waveforms here. So as you can see, this is about 11 milliseconds from 0.306 seconds in the overall waveform for the sound file to 0.317. Okay, so, and this is basically the same no matter what our sampling rate is going to be. However, there's a little bit of a tweak that happens. So in the second version of this, where I reduced the sampling rate by 1/10 to, didn't write this out appropriately, where I reduced this, put a sample at 441 hertz. So I reduced the sampling rate to 4,410 hertz. And in that case, I have just 1/10 as many samples as I had in the original. And so in this case, if I take samples that correspond to these, 1350 to 1400, I'm going to get 51 samples. 50 to 100 includes 51. And then divide that by the overall amount of samples you get in a second. It's 51 divided by 4410. I get 0.01156 seconds. So it's not totally exactly the same number here because we're losing some information basically. So time is going to get a little bit of fuzzy as we do this. Also, the representation of the sound can get fuzzy, which is a little more important for our purposes. So what I'm going to do next is cut this the sampling rate for this representation by 1/10 yet again. So we're going to bounce down to 441 hertz sampling rate. We'll see what happens. And this is also going to give us a chance to kind of look at this at maybe a simpler level that is easier to understand. So I'm only going to take every 10th sample of this one. There's 51 total. We're going to wind up having 6 samples here at the end, and I'll show you how that works. So this is our first sample at 0.306 seconds or thereabouts. This is our second one. And again, these have to be evenly spaced in time. So at each point in time, again, evenly spaced, I just look at what's the amplitude value and I record that. And then if I want to, I draw this line in between the different values and I get a representation of the waveform. Like we saw before, we're going to miss a lot of information. So for the first 2 samples, I'm just going from here to here. What I'm going to get out of this is just this straight line. I'm going to miss all these up and downs here at the beginning. I'm going to miss all these up and downs here in between the second and third as well. Instead, I'm just going to be left with this, right? Because I reduced the number of samples by 1/10. So these are samples 135 to 140 of the same file. There's 6 in there. That's what it looks like. But this is basically what I mean when I say that we're sampling. This is kind of the essence of the acoustic to digital conversion process in a computer. Hopefully that makes sense. But if it doesn't, you can rewind the video and watch it again. Or you can ask me questions. I'm going to ask you a question. I said sampling rate is the frequency at which samples are taken. This is a rhetorical question because I've already kind of given you the answer, but what's a good sampling rate for speech? Typical options you'll see are at the low end like 22,000 hertz or 22,050 specifically. 44,100 hertz, that's what our sound file was originally sampled at. 48,000 is another popular option. Sometimes nowadays you see systems go much higher than that, like 96,000 or 192,000. Theoretically, you can go as high as you want, as long as you have the computational power to do it, and computers could easily do this if they wanted to. But should they, is the question, really. So like I said, a lot of people get upset that you will wind up losing information if you don't sample enough, like we did with our final representation. We lost a lot of information in that one. Normally speaking, we want to go a lot higher than 441 hertz. Like I said, the default for prot is 44,100. Those higher sampling rates are going to preserve the sound quality. They can preserve more of the information in the original analog signal. Lower sampling rates you might want to use if you had a problem with saving disk space. So on computers like laptops or desktops or what have you, saving disk space is not really an issue like it used to be when they kind of started developing these methods back in like the 80s or around that time. So you don't really have to care about that. When you record sounds on your phone, though, or another device which maybe doesn't have as much storage space, then the engineers will start to do some clever things so that they don't have to store quite as much information as we might want when we're doing acoustic phonetic analysis. So yeah, on your laptop, you don't have to worry about this, but normally you'd record at around this rate. Why is that? It's because young, healthy human ears are sensitive to sounds from 20 hertz on the low end to about 20,000 hertz on the high end. So what's the connection between 20,000 hertz and about 44,100 hertz sampling rate? The connection is Harry Nyquist. So Harry Nyquist was an electrical engineer back in the 20th century, and he discovered this property that we have to consider when we're converting any analog sound to a digital representation. So this property is known as the Nyquist frequency. The Nyquist frequency is the highest frequency component that can be captured with a given sampling rate. And it turns out that it's 1/2 of the sampling rate. Before I tell you why that is, I will mention good old Harry Nyquist. Normally I want to present like personalities in class who have made some sort of profound contribution to our understanding of phonetics. I tell you some sort of interesting biographical info about that person. I have yet to be able to find anything interesting about Harry Nyquist. So I'm just going to say he was a good guy, and I'm glad that he figured this out because it helps us all out a lot. But, you know, engineers, not always super exciting people. They're just reliable. Okay, so what did he learn? Harry Nyquist learned that you have to basically, to capture any frequency component in the original analog signal in your digital representation, the highest frequency component you're going to be able to get is 1/2 of your sampling rate. So let's say I have a 100 hertz sine wave that looks like this. So I'm getting 100 repetitions of this pattern every second, and I record that with a 100 hertz sampling rate. Then my sampling rate is going to coincide with sort of the repetitions of the sine wave pattern. So let's say my first sample is here right at the peak of one of the sine waves. My second sample is going to be at the peak of the next sine wave cycle. The third sample is going to be at the peak of the next sine wave cycle. The output representation of this conversion process is going to be a straight line. It's not going to look like a sound at all. I'm just going to get a consistent amplitude value throughout. So this doesn't work. I'm not going to get anything about this underlying back and forth pattern in the sine wave in my sampled version of the sound. So I'm losing too much information here to have any sense of what's going on here. If I want to get that, I need to get at least sampling rate that is at least twice as high as any frequency components in the signal that I want to capture. So in this particular case, I have a 100 hertz sine wave. If I sample this with a 200 hertz sampling rate, then I'm going to get sort of both the bottom and the top of the pattern. So I can get at least some sense that this is a sine wave, that this is a periodic alternating pattern in the signal that I can represent in my digital representation of the sound. So here's my first sample. It's at the valley of this sine wave, the bottom of it. Next one's going to be at the top, and it's going to alternate back and forth. It's going to look different. It's going to look jagged. It's not going to be nice and curvy like a sine wave is, but we're at least going to get it to bounce up and down and be periodic that way. It's going to be something that's repeating, a sine wave that has a repetitive periodic pattern. Okay, so that's Nyquist frequency. The highest frequency component that you can capture with a given sampling rate is 1/2 of the sampling rate. So if I am going to sample with a sampling rate of 44,100 hertz, the highest frequency I can capture is half of that, right? It's going to be 22,050 hertz. So normally I would recommend that you use sample speech at least that rate, because remember the high end of our hearing is going to be about 20,000 hertz. So you're going to get at least that and a little bit more. There's a little bit of fuzzy area at the end. I'm not going to go into that. So it's easy to do this, and I'd recommend that you do. I'll give you some different examples of what different sampling rates sound like, though. Normally, there's not much important in speech. We've seen this when we look at spectrograms. There's not much important information above 10,000 hertz. So if you want to sample at this rate, you could get away with it without losing much of anything of interest. But it's basically no cost to you to go up to the higher end and do 44,100 hertz itself. So let's listen to these. These are borrowed from a friend from a long time ago. They might be amusing.
I find it hard to believe that you sound better than you look.
And this one.
Dirty rats are the best, aren't they?
Yeah, I don't know why she said that, but she did. Let's listen to how the sound changes as we decrease the sampling rate.
I find it hard to believe that you sound better than you look. Dirty rats are the best, aren't they?
So it still sounds pretty good, right? It might start to decrease in quality as we do this.
I find it hard to believe that you sound better than you look.
Or this.
Dirty rats are the best, aren't they?
Yeah, so you're starting to lose some information for the S. S normally has the highest frequency energy of any speech sound we can make. So those S's aren't coming through quite as well as they used to.
Dirty rats are the best, aren't they?
And then we keep going.
I find it hard to believe that you sound better than you look. Dirty rats are the best, aren't they?
And it increasingly starts to sound like she's speaking into a tin can.
I find it hard to believe that you sound better than you look. Dirty rats are the best, aren't they?
Right, so you're not just losing the S information there, but some other information as well, and it does not sound that great. So that's the sort of information you lose. Actually, this is something I normally like to point out, but forgot. If we go back to this original representation, you might remember we had this nice smooth curve and these little bumps throughout. These little quick bumps in the waveform, that's high frequency periodic information. Stuff that changes very quickly over a matter of a few milliseconds is high frequency. So when we convert this to a lower sampling rate, that's what we start to lose. It starts to get smoothed out a little bit. I'm not going to go through all the different samplings there, but you can see those bumps are what gets lost when we go to a lower sampling rate. So that's kind of like the equivalent, the visual equivalent of what we heard when we lost that S information on these demos. Okay, this is another problem that's mentioned in the textbook that you don't have to worry about this so much because the engineers take care of it at the back end when prod digitizes signal for sound waves for you, but it's called aliasing, and it's kind of interesting just to think about. So when you have a continuous sound signal completing more than one cycle in between samples, like we've kind of seen before, where you're kind of missing all this information in between these dot samples, it's possible that the output signal, the converted signal, can contain a low frequency component, which is not actually in the original. So the original here is this fast bouncing up and down sine wave. I'm taking samples where I see the black dots, and it just so happens to line up in a way that these samples I took in the end wind up looking like a sine wave, which has a much lower frequency. So if I do the math quickly in my head, this is 10 milliseconds, and I'm repeating one cycle of the sine wave here. So that should be a sine wave of 100 hertz. This one, however, is bouncing back and forth. It repeats 5 cycles in the same time frame, so this would be a sine wave of 500 hertz. And for some reason, I am sampling at a very low rate such that I'm not able to capture that 500 hertz sine wave. There's another reason why you don't want to sample at a very low rate, because you could get this sort of artifact of an alias low frequency sine wave, which is not in the original. Okay, so whenever sound is digitized, the solution to this is that frequencies above the Nyquist frequency should be filtered out of the end product. So if you, I don't think people listen to CDs as much as they used to anymore, but that was kind of the gold standard of acoustic quality for listening to music, at least in some people's recent memory. So CDs digitize at a 44,100 hertz sampling rate. So they'll be able to capture anything from 22,000 hertz down. But before they do that, they filter out any components above 20,000 hertz, just to make sure they don't get back in there through aliasing. So this brings me to the topic of filters. There's different kind of filters you can use to sort of change the frequency structure of speech or whatever sound wave you're looking at. On the one hand, we have what are called low pass filters. And it's tricky for me to remember these, which is why I'm trying to make a big deal out of it for you guys. So low pass filters will allow low frequencies to pass through the filter, and they get rid of the high stuff, which is what you do when you make a CD. You filter out stuff above 20,000 hertz. That's a low pass filter. You could also have a high pass filter, which does the opposite. So that allows high frequencies to pass through the filter, and it gets rid of all the low frequency stuff. There is a representation in the textbook, which looks like this, which shows you the power spectrum of a 100 hertz plus 1000 hertz complex wave. And the filter is just saying, well, we're going to keep this guy and we're going to get rid of that one. I'm going to try to show this to you in prot, maybe a little more dramatic and or interesting. So I'm going to grab this production of the word sampling that I played for you before.
Sampling.
Okay, that's what it sounds like normally, and actually we can look at this in terms of its spectrum. Why don't we go all the way up, see how good my microphone is. So this is up to 20,000 hertz.
Sampling.
And actually I've never done this. Might as well give it a shot. What happens if we go up to 40,000 hertz? Yeah, so you can see this cutoff frequency. Boop. It's a little above 20,000 hertz. So my microphone or the sampling rate is not able to capture that frequencies that high.
Sampling.
You can see, however, this nice S here has a lot of high frequency energy. The rest of this is mostly vowels.
Sampling.
And a P in the middle. So yeah, that's what sampling rate gets you, or doesn't get you, rather. What I'm going to do is I'm going to filter this. So I'm going to go to this filter function in prot, and I'm going to use what's called a pass handband. So the default here is to pass everything within 500 to 1000 hertz. That's actually known as a bandpass filter, because it just gives you a certain range of frequencies. It passes through a particular bandwidth, as it's called. I'm going to make this a low pass filter. So I'll start out like we did before. I'm just going to pass all the frequencies below 10,000 hertz. We could take a listen to that.
Sampling.
And it probably doesn't sound that different from the original.
Sampling. Sampling.
But if I look at this, my cutoff frequency is a lot lower. It's around 10,000 hertz. And I'm actually going to change this so you can see that better. Yeah, so this is at about 10,000 hertz. My higher upper end of the range here is 15,000. It cuts off at 10,000.
Sampling.
And there's still enough of the S in here that it's not a problem. So let's look at the lower end of this S. It's at about 3,600 hertz. So I'm going to filter the original again, but I'll filter it so that it only includes frequencies from 3,500 hertz below. And we'll see what that sounds like.
Sampling. Sampling.
Yeah, so
Sampling.
I've kind of lost my S there. It sounds a little bit different.
Sampling.
Maybe it even sounds like a theta. Sampling.
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 I don't know. Maybe I was able to fool you into perceiving that. We can go to our kind of usual setup for spectrogram frequencies in prot, like 5,000, and we can see this cutoff frequency now pretty easily. So there's a little bit of fuzziness. That's just the way the filter works.
Sampling.
But I don't get that nice high frequency, high intensity energy for the S anymore. We'll go one more step. Actually, we'll do two different things. We'll go all the way down to like 1,000 as our cutoff frequency. What does that sound like?
Sampling.
Yeah.
Sampling.
There's that tin can effect. So we're not getting a lot of information or energy for the vowels here either.
Sampling. Sampling.
It's like this is what happens when you can only hear F1. We'll do it one more time. I'll give you the high pass filter option. So we'll start at 3,500 and just say you can give me anything above that. What's that sound like? Yeah. So you can hear that S nice and clearly now. The vowels and the rest of it don't sound good at all. So here's my S. Here's the rest. Yeah. Okay, so that's how filters work. I'm not going to say anything more about that. I will simply move on to the last thing we need to care about, or know about and care about, which is quantization. How do we digitize the other dimension in a waveform, which is the pressure dimension or amplitude dimension? So each sample that is taken has a range of pressure values. And like I said, everything in a computer needs to be represented in terms of a 0 or 1. Each representation of a number as a 0 or 1 is called a bit, or it's a sort of it's a piece of information that's allotted in the computer's mechanical brain to represent a number, and it has to be, it's basically a circuit which is either on or off, and it represents a number that's either 0 or 1. So you might recall this if you learned about representing numbers in the binary system in math class back in the day. So computer is going to store all numbers in terms of binary format, which is basically a sequence of ones and zeros, and each slot for a 1 or a 0 in the representation of a number is called a bit. So if you have 8-bit encoding and you want to represent the number 89, this digit represents the 1's digit, this represents the 2's digit, this is the 4's, this is the 8's, this is 16's, this is 32, 64, 128, so on and so forth. It goes up by a factor of 2 each time. So this is 1, this is 8, this is 16, this is 64. So 64 plus 16 plus 8 plus 1 is 89. That's how a computer does it. And it's not just counting whether there's a 1 there or not. It has to allot one slot for each of these possible 1s or 0s. So there's 8 different numbers in this representation, even though some of them are 0s. So that's what we call 8-bit encoding. If you do the math on this is 128 plus 64, so on and so forth. You can get basically 256 values. If you have 8 bits, that's 2 to the 8th power. I'm going to post a handout about this, and I'll post it online. I'm not really going to walk you through it. You can read it, though, if you want to, if you are worried about what this all means. It's not that important as long as you get the general sense of it. If you have 12-bit representations, that's 2 to the 12th, or 4,096 values. 16-bit representations can give you 65,000 plus different values of numbers. So basically it's saying for any particular sample that I get from my sound wave, I can have in a 16-bit representation an amplitude value which ranges from basically 0 to 65,000 of some sort. So there's a lot of leeway there. There's far less different amplitude values you can get if you just have 8-bit representation. There's only 256 rather than 65,000 plus. So I'll show you what that means in another way with going back to our maximally reduced representation of this guy.
Sampling.
So let's say I am going to sample this snippet with 3-bit quantization. So that's 2 to the 3rd power. 2 times 2 times 2 is 8. So I can get 8 different possible sample values. I'm going to cheat a little bit here because this is just the easiest way to represent this in Excel. But so I've got 4 different possible values on this side. Go back a step. The point I want to make here is when you quantize a waveform, and you're doing with a 3-bit quantization, the output amplitude values can only take one of 8 different possible sample values. So I said I was cheating a little bit. There's 4 different possible amplitude values on this side of 0. There's 4 over here, and there's 1 in the middle, so 9, but it's basically the same idea. But basically what I'm saying is each of these samples, no matter what its actual value is, what its original value is, I'm just going to pick the line that's closest to that amplitude value and say that is my amplitude value. I'm going to simplify my life a little bit. I'm going to reduce my amount of sound that I have to represent by just saying it's got to be one of these different 8 values. So when I take my first sample, that one's nice because it's basically right on that line. Second one, not so nice because it's not really on either one of these lines. It's got 2 that's close to it. I'm just going to pick the one that's closest to it. So I'm going to say, well, that is my amplitude value here. And we know, because we have this God's eye view of things, that the original is down here, but that is not what the computer sees. The computer says, well, it's here, so I'm just going to squeeze it up here and say that's what it is. The next one, the line it's closest to is 0, so we're going to say it's right at 0. This one is kind of in between these two, but it's a little bit closer to 0, so we're in 0 again. This one, the closest one is this line, and then the last one, the closest one is 0 again, although it's a lot closer than these previous examples, right? So the ultimate representation I get is going to look like this. So you can see it's fairly close to the original, maybe not so great here. But basically I have to squeeze it to one of these different 8 possible output amplitude values. That's what I do when I'm quantizing things. And it looks fairly similar to the original, but obviously not exactly the same. So this is the final product. Hopefully you can see how I made that conversion. We could try it again with a slightly higher bit depth, as it's called. So I'm going to use it with 4-bit quantization this time. In other words, 16 possible amplitude values. So I've got, again, I'm cheating. There's 8 on this side of 0, 8 on this side of 0, and I've got 1 here in the middle, so 17, but it's basically the same idea. So basically, I'll walk through this again, and for each sample, I want to pick the line that is closest to the original, and this one's basically right on it. This one, maybe a little bit closer because I can pick this value of 0.05 now. So I'm going to say, well, that's that amplitude value. Again, not the original, though. That one's there. That one's at 0.05 this time. We get a little better reading for that one. This one's right there. This one's right there. This is going to look a little bit closer to the original than my previous quantization. There's still a little bit of a gap in between the orange line and the black line, but it's pretty close, or at least as close as we can make it if we are allotting this number of bits to each sample in our computer's representation of the sound. Okay, so it looks like that in terms of finished product. Okay, so note that when you do this, you're normally going to get some rounding off error for each sample. It's not going to be exactly right on top of it. Maybe in some rare cases it will be, but that's the exception rather than rule. So you get a little bit of rounding off error. There's a little bit of gap in between these two lines. So what happens is that emerges as what's called quantization noise in the output file, because you can actually hear that rounding off error in the quantized sound file. It's like you're adding a little bit of incorrect value to the original, and it's not sort of something that's predictable or periodic, so it sounds like noise. It sounds like randomness for each sample that you get. So I plotted on this 4-bit quantization the noise that kind of gets added into the signal, which is the rounding off error for each sample. It's in this gray line here. So to the extent that this deviates from 0, you're going to hear it as noise. It's going to be sort of like its own waveform. And I've plotted this for the 3-bit quantization as well. Normally, you expect a little bit more noise for lower bit depths of quantization. I think I might actually get a drink of water here. Excuse me. Speaking of noise, you probably don't want to hear me cough. Okay, so here's another example from the book where you see noise kind of plotted on top of a nice sine wave pattern. So this is what you have to do when you quantize this sound file. You can only take these values here at these various levels. So this looks like a jagged version of a sine wave instead of a nice curvy version. And the noise is plotted here in the middle, and it's basically the difference between the original sine wave and sort of the jagged version. And it doesn't look pretty, like nice and periodic or sensible or what have you, and it's not going to sound pretty either. So I'll give you some examples again from these demos. So this is an 11,000 hertz sampling rate and then 16-bit quantization from the samples we heard before.
I find it hard to believe that you sound better than you look.
So you can't quite hear it yet, but it'll be coming on the next one.
Sturdy rats are the best, aren't they?
So listen closely to this.
I find it hard to believe that you sound better than you look.
So hopefully you can hear that static kind of in the background. That's the quantization noise.
Sturdy rats are the best, aren't they?
And it's kind of competing with my fridge in my background, but hopefully you can hear it coming through the computer. Let's reduce the sampling rate even further to 8,000 hertz, and this is what it sounds like for 2 different bit depths.
I find it hard to believe that you sound better than you look. Sturdy rats are the best, aren't they?
And if you can believe it, a good old-fashioned telephone will digitize at 8,000 hertz sampling rate and 8-bit quantization, and it'll sound like this.
I find it hard to believe that you sound better than you look. Sturdy rats are the best, aren't they?
Yeah, so the quality is poor, and it always kind of mystified me. That telephone system was created, in the early 20th century, and it hung around until kind of cell phones took everything over. But it was always kind of a mystery to me as to why people put up with quality that was that bad for so long. I say this as somebody who almost never uses a cell phone, but be that as it may, it's good to know that we're now doing better with things like Skype and what have you. CDs, as I mentioned before, they sample at 44,100 hertz, and they have 16-bit quantization. Computers, so I'll give you an example of kind of what it sounds like on a phone versus Skype. So these are some old samples that I recorded a long time ago. One from a former girlfriend who maybe doesn't want me playing this, but we'll do it anyways.
Well, okay. It was also acted out by a whole bunch of creepy people.
So yeah, we used to have conversations on Skype, but you can hear in this one, it's pretty decent quality. You can just kind of hear a little bit of reverberation in the room, that kind of bit of an echo after she says things.
Well, okay. It was also acted out by a whole bunch of creepy people.
I think she's also typing there. That's something separate. This is a phone conversation with my brother. He and I normally like to talk about sports. So this is from a while back, talking about Adam Vinatieri, field goal kicker for the Indianapolis Colts.
This is me. I was wondering if you've seen that stupid, terrible game where Vinatieri missed a chip shot field goal. I think we're going to have to look for another field goal kicker, because that looks pretty bad.
I also like this one because both my brother and I lived in Chicago for a while and picked up a bit of the Chicago accent, including on the kind of shift of the vowel "ah" there in bad.
That looks pretty bad.
Bad. So that's kind of nice. But if we zoom in, you can see what happens when he speaks over a phone is he's basically losing all information over about 3,500 hertz.
That looks pretty bad.
And yeah, the quantization is what it is. I don't have a nice quick and dirty way to show you that. We can compare that to this. As you can see, the frequency information goes much higher when you're talking on Skype or something like that. Her microphone or sampling rate was cutting out around 9,000 hertz. So
well, okay.
Yeah.
It was also acted out by a whole bunch of creepy people.
It's better, but maybe not as good as like a CD. It's definitely good enough for you to understand what she's saying, though, right? Okay. So how do we think about this? So quantization range. With 16-bit quantization, we can encode 65,000 plus different possible amplitude values. So if you think about this in terms of another formula we learned about in 341 for intensity, that is expressed in this fashion. So I'm going to sort of replace this variable here, amplitude, with sort of the equivalent range of different amplitude values we can get from quantization, and show you that you can get a range of about 96 dB when you quantize at this bit depth, which is really quite good. Basically, the quietest sound you'd normally hear in normal living is like about 30 dB, and the highest end that you wouldn't really want to, but 120 dB, 126 is kind of at the level where it's starting to possibly damage your eardrums. So that's kind of why CD manufacturers pick that range, I think, because it's a reasonable range for normal life. Newer machines have 24-bit quantization. I haven't seen too many machines that go higher than that yet. But this will give you 16.7 million possible amplitude values, and that would give you a decibel range of about 144 decibels, which is easily enough to record anything you might want to hear as a human being. So yeah, like I said, this is bigger than the range of sounds you can listen to without damaging your hearing. You're fine if you go with this. If you want to go bigger, it's also probably fine too, because you're not going to listen to something that loud, I'm pretty sure. At least not for this class. Okay, so one problem you can get if you don't sort of make your quantization range as big as it should be is called clipping. That's when the pressure in the original analog signal of a sound exceeds the sample size range in digitization. So you see this easily in a waveform because basically the tops and bottoms of the periodic waveform are getting sliced off by the digitization process. And so it's going to look like it's basically flat at the top when it should be a nice up and down curve. So you can kind of hear that in this sample.
Marilyn won $9 million.
There's that kind of buzzing as she's saying that. Here's the original without the clipping.
Marilyn won $9 million.
It sounds pretty good. This is what you get when you get the clipping. You get that buzz.
Marilyn won $9 million.
It's subtle, but it's there and doesn't sound too great. I can give you some more obvious examples. Yeah, so I'll just play this one. Yeah, this one's subtle as well. Go with 5,000.
Yeah, the thing is that, like, if you only met him for like a day, you would think he was totally normal.
Yeah, she might have been describing me. I don't know. Either way, there's a little bit of clipping you get here at the top and the bottom of this one because she's saying it quite loudly.
Yeah.
And you can hear that little ringing a little bit in the recording. More obviously, we get this.
I taught putty tat.
So with this P,
Putty tat.
I'm just popping a lot of air into the microphone, and you can see it cut off here at the top and the bottom. That's clipping.
Putty.
And it doesn't make it sound good. So try to avoid that from happening if you do make a recording of your own as you work through, say, your course project for this class. Usually the easiest thing to do is just have the person not speak directly into the microphone, like over here, so that they're not sort of pushing a bunch of air into the diaphragm of the microphone. One last note. Hopefully this hasn't gone on too long. So much fun to talk about. But digitized sound files come in different formats. You may have noticed this. In Prot, you can save sound files like a WAV format, IFF. AU is a format that used to be, well, relatively popular. Either way, there's a lot of different digital sound file formats. What does it matter to you? These appear like WAV and AIFF. WAV is a sort of a for PC format, and AIFF is sort of a Mac proprietary format. But what these formats are called are lossless because they digitize sound in the way I've just described. So they only differ in terms of what are called the header information. Basically, each file has to have some information the computer needs to know in order to interpret the different amplitude and time values in the representation. Otherwise, these formats will digitize sound just like I've described, trying to preserve information in sort of the most veridical way. You can compare that to what are called lossy formats, which use algorithms to condense the size of the sound file. So if you're really storing, one individual value for each sample with all the different quantization values, it can start to eat up memory fairly quickly if you have sort of a machine that doesn't have a lot of space devoted to storage on it. Normally, again, for computers it's not a big deal, but for like phones and other devices it might be. So these devices, and this is also a case back like in the 90s, would use lossy formats to condense the size of those sound files, and they wouldn't be sort of faithful to the original in the same way that these lossless formats are. So for instance, the MP3 format, which came out like in the late 90s, became quite popular quite quickly because it was dealing with an internet that couldn't transfer information quite as quickly. That saves space by eliminating some very high frequency information. It also kind of messes with the time information a little bit too, but it usually does so in a way that's hard for people to hear, so it can get away with it. And so, like I said, this became popular back in like the Napster days because it was a way for people to basically post music online and get it for free. This may be hard for you youngsters to believe, but back in the old days, getting music that you could listen to on demand was not easy. You had to have like a collection. For my parents, they had a record collection. I had a tape collection, which is still gathering dust in my basement because I don't ever give it up because it was hard to get music. And MP3s made that easy by being a little bit clever computationally. So this is an example of some music in 3 different formats. So this is the AIFF format. This is a song from Bruce Springsteen, which starts out with some drums, so you can kind of see the timing nice and clearly. Okay, so that should sound relatively decent. This is an MP3 format. And you can see, so I've shown you the spectrogram all the way up to 20,000 hertz here. You can see it cuts off like at about 15,000. And the timing looks a little bit like faded out here a little bit at the top too. We can listen to it. Yeah, so and then it's also converted to your machine through my recording software as well. So hopefully you're able to hear that okay. But there's not that much of a difference. Maybe if you listen really closely, you might be able to hear it. I can show you another version though, which is MP3 digitized at kind of a lower bit rate, and you can start to see it in the spectrogram here. The frequency scale is the same, but you're losing more information, and you'll be able to hear it this time. I just wanted to go to the vocals there because the vocals are still pretty decent, but the drum stuff is just kind of messed up, both in terms of timing with a little weird echo and whatnot. So MP3s, if you push it, can start to sound bad, but if you allot enough space to them, they can kind of help you save space and also get music that sounds pretty good. Okay, so with that, what I would basically recommend is that you, for this class, if you're recording anything, please record it in this format, because ultimately I'm going to want you to do acoustic analysis of whatever you do record, and this is the best representation to do that in. So I mean, I'm not saying AIFF, I mean lossless formats. So normally we record in WAV, you can record in WAV, you can record in AIFF, just don't record in MP3s. If you have some sort of little personal handheld recorder, it's probably going to give you a lossy format like this. Don't do that. Record in PROT if you can. So to wrap this all up, samples are taken of an analog sound's pressure values at a recurring sampling rate. This digitizes the time dimension in a waveform. Sampling frequency that you use needs to be twice as high as any frequency components you want to capture in the signal. So a good rule of thumb for that is something like 44,100 hertz for speech. Quantization is going to convert the amplitude value of each sample into a binary number in the computer. This will digitize the amplitude dimension in a waveform. So we're basically binning up the original into the time dimension and also the amplitude dimension. And when you quantize things, there's one possible error you can get there, which is quantization noise, which are due to rounding off errors. And then excessive amplitude can lead to clipping errors. And the moral of the story is that, again, when we're dealing with sound in a computer, we're using a representation based on the original analog reality, but it's not exactly the same thing. If we do it well, it can be basically treated like it's the original and we don't have to worry about it. But remember, it's not exactly the same, and there are illusions that the computer can create which can deceive you. So as long as you know where they might be coming from, you should be okay, but just be aware. I think I'm going to stop for now because I've talked for long enough, but I'll catch up with this again on the next lecture. So see you then.